And we'll start, sir.
Yeah.
Yeah, very good evening, all distinguished guest faculty, research scholars. It is my pleasure to introduce our esteemed guest speaker for today's FDP, Professor M. Joseph Davidson. Professor is a distinguished faculty from Mechanical Department at NIT Warangal, and he holds a PhD degree in non-ferrous materials technology from prestigious NF in Hyderabad. He worked as a heritage fellow at esteemed Warsaw University of Technology in Poland for a brief time. And Professor is a prolific researcher with a strong publication record, boasting over 80 research articles in various renowned peer-reviewed journals in international journals. His dedication into research is evident in his successful supervision of 14 PhD scholars, and Professor Davidson's contribution to field of material science have been duly recognized. He was honored with the prestigious Best Young Researcher Award in 2014 by NIT Warangal. Today, Sir is going to share his expertise on the cutting-edge topic, that is ML models for automated analysis of grain size in metallographic microstructures. And this insightful presentation undoubtedly going to provide insight into the application of these ML techniques in material characterization analysis. With this brief introduction, please join me in extending a warm welcome to Professor M. Joseph Davidson. Sir, please, session is yours.
So good evening, and I'd like to first of all thank Dr. Nalinikant and Dr. Rajesh for giving me this opportunity. And I also warmly welcome the participants. I understand the participants are from different departments. So I have kept a bit of introductory topics in AL and also some advanced research topics. And you can interrupt if you want in between also. And I also kept a lot of explanatory slides in the end if you want to know more on any topic as well. So I'd like to cover this topic within 1 hour and 15 minutes, and we can have some discussion for the next 15 minutes after the lecture is over. So to conserve the internet, let me switch off and let me go to the topic. So the topic today is ML model for automated analysis of grain sizes in metallographic microstructures. So in this particular lecture, I'll be talking about an introductory. I'll introduce you to some basic ML models to start with. Then we'll also start with a segmentation model at a basic level, say a small signal. Then we'll go to a microstructure, how to segment it. Then we'll go for an ML model to automatically measure and predict the number of grains and the size for a research sample that we produced. So before starting my topic, I would like to acknowledge my scholars. Basically, I got into AI or ML some 3 years back in 2022-23. My scholar Abhay Ram, who was in fact working on constitutive modeling of thixoforming of ALSI alloys, he was also interested in using some of the ML models. So we started around 2022 without knowing anything. In fact, we started, and I got a good student in the name of Dhanush Reddy, a BTech student from NIT Warangal. He was extremely resourceful for us, to me as well as to my scholar to start with, and presently is working in DP World as an ML engineer. Then subsequently, Hari Krishna, another scholar, he continued the machine learning work. And based on these, we have a few publications. The latest publication only I have kept. In fact, neural network, I started, my first publication is on neural network in the year 2004. So with this small introduction, we'll go to the topic. So before that, a small disclaimer. The ML models or the segregation models that I'm going to talk about, I'll be using the Python built-in models. I have not done any work on improving any of the models. We have not produce any new models. We have used only the already existing built-in model. So any one of you who are interested in doing that work can also do a good amount of work and publish papers with the existing built-in models itself. So the disclaimer is we have not done anything beyond what is existing as of now as far as ML is concerned. Only thing we have done is we have applied the existing model that suits the problem that we deal with. The topic is ML models for automated analysis of grain sizes. So obviously we'll be having a microstructure. The microstructure manually will measure the grains, and we should be able to produce the same amount of grain with the number as well as the size using the ML models. This will be my time schedule. I'll be doing a small amount of introduction on machine learning and grain size analysis. These are all for very few minutes only. Then on segmentation and a case study on image segmentation, filtering methods, and a detailed study on a segmentation method of an existing problem. Then a small introduction about ML model. As everybody is aware of, machine learning, it works on data. What type of data? Data can exist. The data can join in between. Some of the data we can delete in between, and some of the data we can generate also. So if the data is there and if it is good, we can take some of the data for testing. If a good amount of training has been done on the algorithm from the existing data. With that, we can train a model, and during this process, if you feel at any point of time that more amount of data will add more insight into the problem, then real-time data also we can bring in. So machine learning, it is a subset of AI. It focuses on building algorithms and models, and these algorithms and model, they enable the computers to learn from the data. What we do prediction. We take decisions based on the insights thrown by the algorithms by taking the data that we have given to the system. What's the beauty here? Normally, when we have a set of data and we use our mathematical formulas on it, if a new set of data arrives in, then we have to redo it, recalculate it to arrive at the conclusions. For example, I have a set of data. I take the mean, median, and mode. I have a new set of data coming in. Again, I have to calculate. I have to find the sum divided by the number of samples and other things. But the beauty of AI is, or machine learning is, the system continuously improves over time and it adapts as well. For example, if we have a data for a week, you take a test sample for a day, say Monday, and you have a particular set of data. And the subsequent days, because of certain problem in the system, the data was not coming properly and it was erroneous, let us assume. So if you do in the conventional way of interpreting this data, it will always be the same. We cannot modify it. And if the new set of data, we have to again recalculate and we have to use. Whereas in machine learning, the second week and the third week, if the data is good, if the system behaves properly and shows real-time data, then the system automatically adapts. The machine learning model that you build on, it automatically adapts. So the first week data, when you try to predict, it will give a erroneous result. It may not be apt, but more and more apt data is added to the system automatically improves over time and it also adapts to the situation. That is the beauty of machine learning. And machine learning, there are different types: supervised, unsupervised, reinforced learning. Like that, there are different types. In this particular lecture, I am going to use supervised learning, and in particular, I am going to use classification as well as regression. So we'll try to classify the images that we get and make it into a set of subset of the main problem. Then using that particular data, I try to predict or fit an equation and try to predict the size of the grains. That is what we are going to do. So what we do, we will formulate the problem from the system. And for the particular problem, in this particular case, I'm going to predict a microstructure, the grain size of a microstructure. So I will take in lot of samples. I put under microscope, take lot of data. My process will be on one side. I will have lot of process variables. All the process variables will throw in different set of microstructures depending upon the process. I take that and collect as much of data corresponding to the process and then prepare and analyze the data. Meaning for every process that I work on, I'll try to take at least one or two microstructures from it, good one, some bad one as well. Then I'll prepare the set of or a repository of data that can reflect the process that I am doing. In any manufacturing process, I'm a mechanical engineer. We do a lot of metal forming work. So from the metal forming, whatever process developed from me, that microstructure that we get, that we prepare as a set of data. Then for the particular set of data, as I told you, there are several types. What suits us, we have to choose. In our particular case, I need classification algorithm. To predict, I need a regression algorithm. So I'll select appropriate algorithm. And using the image data that I have, I'll train the system. I'll run it and try to predict that type of grain that I used to get. So to have a quick view of what the different type of algorithms are, as I told you, there are supervised learning algorithms. So this supervised learning algorithm needs a data that fits in or predicts exactly, or it fits in the input and the output. That should be a fit. Meaning the set of data that I give in the input, we should have a correlation in the output. So we call that as a labeled data. Labeled data is not just giving some name or something like that. It is like data, that particular value or its characteristics we know, and what it can produce as an output, that also we know. So the model is trained using labeled data, where each input is paired with a correct output. And the goal to use this is to land the relationship between the input and the output, and to make predictions on new and unseen data. So I have a set of data. I am interested in finding out data which I have not trained, but I'm interested in knowing. And common algorithms of this class are linear regression, decision tree, support vector mechanisms, and all those things. And we have another thing called semi-supervised. The next one is unsupervised. In unsupervised, we won't have explicitly, we won't have a labeled data. That means this model is trained on data without explicit labels or predefined outputs. It tries to identify patterns or structures within the data. So you give a set of data, it tries to understand on what pattern this data is of. So it tries to characterize or in a way put a stamp on the data that this data is behaving, it will behave this way, or this will be of this character, like that. The beautiful example is a k-means clustering algorithm. You give a lot of data inside, and this algorithm segregates the data into a bit of island and try to find out the distance this particular problem set is varying with each other, and tries to flock together a set of data, which is closer to itself. That means it chooses a leader and tries to flock towards it. Meaning, say for example, there is a density, right? So I have a density of 2, I have a material having density of 9, I have a material having density of 16, and several within this range, 2, 2.5, 2.4, something like that. So it tries to flock toward the 2 will all tries to flock toward this 2, and whatever is around 8 or 9, it tries to flock toward that 8 or 9. So something like this. So it clusters, it forms clusters, it forms a group, and trying to put inside. Meaning, we have not explicitly told that the density, a material having this much density belongs to this category or that category, like that. The algorithm itself, by finding out the distance, we just choose a leader and tries to find the distance from that particular thing. It tries to find the distance and the least possible distance among the leader, it goes and flocks together. So that we call it as unsupervised. Then we also have semi-supervised, is a mix of supervised and unsupervised. Then we also have a model called reinforced learning, wherein the system takes output periodically and tries to learn from it. In this particular case, we are going to use supervised learning, particularly classification, because we are going to have a set of microstructures and we are going to analyze its characteristics and classify it, how it should behave, how this is, like that we are going to classify. So in the particular problem that I am going to deal after some time, we are going to use the supervised learning as well as the classification type. So what we have for a classification, for a supervised learning, we need a labeled data, meaning there should be a correlation between an input and an output. A beautiful example is an email. If someone says you have won $10 million, then obviously the system identifies that it's a spam and it puts into the spam folder, because it reads the content and anything that is objectionable or doubtful, it can identify and label it that this data is so, correct? So this is how. So it finds the correlation between input and output and stamps that as this particular character. So for classification, we need labeled data. In our case also, we take the microstructures and we give them certain set of characteristics. We associate that with each and every microstructure. That means we are defining the system that if this is round or elongated or this having this particular structure, it is this, like that we train the system. So that means it is a labeled data. And it can be continuous as well as discrete also. Discrete is like particular data only it gives. It cannot be a continuous one. And again, this classification can be of three different types. It is binary, multi-class, and multi-label. Binary is either this or that, either it is good or bad. In the multi-class, this data will classify or associate the characters to a particular class. For example, in this particular case example, the data is identified with cat, dog or something. So it identifies something as cat. In a multi-label classification, a single character can take the form of many. The beautiful example here is, if there is a movie, it can be, there can be some comedy scenes, there can be action also. So some people may see the action part, some people may see the comedy part, but in that particular movie, it is both in fact, correct? So it is a multi-label classification. So such problems, when it comes, we can use these type of algorithms. Data which has multiple characteristics, or you want to associate one-to-one. So all type of problems we can have, use this particular algorithm. So next is the introduction to the grain size analysis. As the core area that we have chosen for this ML model is metallographic microstructures, obviously the grain size. Those who are from mechanical, chemical and metallurgy will appreciate that the material properties, it will be guided or influenced strongly by its grain size. It affects the strength, its surface roughness, corrosion resistance and all other material properties. And every time we instead of going to microscopes and compare that with standard data and measuring its size by putting it under a microscope, if you can simply take a photo and put it into the system and automatically getting a size, will save time. Also, if the system is robust, the system that we have developed, if it is so robust, then we can have accurate results also, right? So that is the idea behind this particular effort. We have tried to create a system which will take only an image and the system takes care of everything. It measures the boundary, it measures the size, it measures the number and all those things. But having said that, is it that easy? Obviously not. The reason is, when you have a structure, when you take a microstructure, there will be some fragmented boundaries. They are fragmented boundaries or irregular or continuous, discontinuous grains. And there can be some fused grains, actually 1 or 2 or 3 grains. Sometimes it will get merged together and we call it as fused grains. And there may be some noise also, noise in the sense, if you don't take the photo properly, or if there is some inherent problem in our microscopes, in our lens, then that particular figure won't be proper. Even such figures, we can, using our AL models, we can use it to measure actually. That is one advantage as far as the system that we have developed is. And then the edge grain, those who are on the edge, mostly there may be a smaller 1/3, 1/5, 1/10 like that. There may be different dimensions of edges, edge grains will be there. So it will be, we have to discard those things. So this system that we have developed or we have done that discards these edge grains also. So there are challenges in fact in image segmentation. Somehow by adopting different techniques, we have in fact overcome. So what we have done, actually, as I told you, metal forming is my core area. So we do a lot of constitutive modeling, meaning at high temperature and different strain rates, how the system behaves, that we make it into a mathematical model. That mathematical model, we put it into softwares like Deform, and we try to predict the properties. So material new combinations we develop, and new combinations of process we develop, and we develop new set of constitutive relations, take into consideration of stress rate, strain rate, temperature and other things, and materials also. And we do, this is how normally we do. We have gone a bit ahead now. So instead of only stopping and developing only experimental as well as a simulation based model, we also gone a bit ahead using AAML. So what we have done, that microstructure that we put inside our system, and we run the system that we develop, and it predicts its grain size, boundary, what type of grain it is, and what is the size, how many numbers of grains are there, what is the area of one particular grain, all such information it gives. So this is a flow chart for this particular problem. We have to occur the RGB image, you have to convert that into a grain scale image. Then there are few techniques like median brush, thresholding, erosion variation, all those things. So before doing that, I have a particular slide for each and every topic. I'll go to that a bit later. Before that, let us go or have a small introduction about how to do filtering and how to do image segmentation using a small signal, right? So instead of going the full-fledged microstructure, let us have certain fundamentals on this image processing. Then I'll go back to the same slide again, and I'll explain to you how things are done. So basically, image processing, it can be divided into two main fields. That is, number one, it is a local filtering. The next one is image segmentation. In local filtering, we apply a filter to a segment in that particular image to enhance its features. For example, if it is dull, we'll improve the contrast. If it is not linked properly, we try to draw a boundary, right? Something like that we do. So that we call it as the filtering. And the segmentation, it is a process of dividing an image into multiple parts or regions that are more meaningful or easier to analyze. The filtering, it helps you to slightly uplift the image and make it suitable for segmentation. In segmentation, we try to make it more meaningful to analyze it. The segmentation, again, it can be done based on color, texture, intensity, and edges. In this particular problem that we have taken color, we have taken intensity, and we have taken edges also. And texture we have not done. We have taken a bit of round image only. If a multi-textured image is to be analyzed, it needs more effort. We are doing it, we are yet to succeed in it. As of now, we have taken color, intensity, and edges as the problem. As I told earlier, the challenges in image segmentation is images normally have a lot of noises. So what is noise? Anything which is not desirable in that particular image, we call that as a noise, a segmented boundary. Okay, a very dull image. All these things are considered noise. And we will also have some contrast variations. What is this contrast variation actually? Some will be brighter and some will be dull. But when I compare my image, the grain should be brighter and the background should be lighter, so that I can easily identify what is grain and what is not a grain. And I cannot go on changing the contrast of the image, because I purposely put some wrong images inside the slides down after some time. I'll show that because if the contrast is not optimally, then the foreground and the background image both will merge. Actually, you won't get any contrast at all. So very meaningfully we have to do. And another important thing is thresholding. As I said, in an image there is a grain and there is a background, non-image, right? Non-image. So I have to identify what is a grain and what is not. And that is done based on threshold. Threshold is like there is an optimal parameter which says beyond this you can do some treatment and below that you cannot. So that is called thresholding. For all these things there are a lot of algorithms. We'll see that later. And as far as the grain are concerned, the images are, the challenges are the fuse grains, the edge grain removal, how to remove the edges, and how to separate the grain boundary. Okay, I have to exactly identify what is a grain boundary, otherwise I cannot measure its size and its number also, right? So these are some of the challenges: fuse grains, edge grain, how to remove it, and the grain boundary. Now, this is a filtering or a method used to remove the unwanted things. The first leftmost thing is the original image, and the middle one is a filtered image. Basically, what is a filter actually? See, you know, a normal filter that you use to segregate the tea dust from tea, correct? So when you use tea, so you use a filter and filter out the dust and take only the liquid tea inside. Like, so similarly in the images also, we purposely make it sometimes dull. Sometimes we purposely make it brighter in order to reveal certain characteristics of this particular image. So for example, so I have a small code to run for you. See, we give an original image. That original image, for example, on the leftmost side here, right? So somewhere here you have a lot of small sort dots here, right? So you have small dots here, and that particular dot, in fact, it is not because of the inherent nature of the grains. It is because of some noise. That area is not properly revealed actually, or it is not properly polished, or there may be some pore, something is inside. So for when I measure it automatically, my code should not treat that as a grain actually. It is not in fact, right? So I slightly hide it, right? So some sort of treatment what I do, that we call it as the what is that, blurring operation. This is the code. I can give this code to you also. I will share with the organizers. So we have done two types of blurring. One is called Gaussian, another is median. So this Gaussian, as you know, it will have a what is that, inverted function, and that will be put over the image. We call it as kernel. We make a small what we call it as kernel on the image that we want to blur it. So we put that and we apply this Gaussian function, and based on the pixel strength that is underneath this Gaussian or kernel, it will be moderated. For example, I put a Gaussian function, weighting function, with a size of 5 by 5 window, let us assume. Beneath this 5 by 5 pixel, there will be at least 9 pixels underneath, a middle one and 8 surrounding things. And this Gaussian blur put the highest intensity in the middle one, and as we go away from the inverted curve, the intensity varies, right? So from the center to the edge, the intensity of pixel will be varied, and this variation will be used to change the moderate intensity of the pixel or the image that is below the kernel that we use. The similar thing is median. It replaces the original pixel with the median value of the mask that we have used. So like that, there are different type of techniques that we use to moderate the image. So purposely, I said that we blur it. Blur, it is like, purposefully deteriorating it the property also we can say, correct? This is also having a meaning like less sharp or out of focus. Now you'll be questioning me. There is an image, it is bright, right? And you say that you want to or you want to purposefully make it blur. That will only deteriorate the property of the image, like that you may argue, right? But there is a meaning actually to purposefully make it out of focus or less sharp. There is a meaning that you will understand a bit later. I'll explain that. So blur in image processing, whether it is Gaussian or median or average, whatever it is used to reduce the noise. It is used to make the figure less sharp, or like it is purposely making it to out of focus. And as I told, there are different types of Gaussian blurs, like Gaussian, median, box, several times. And
I think
yes, sir.
Sanjay Kumar is raising his hand. He has a question, I think. Sanjay Kumar,
Yeah,
you can
yeah.
ask, unmute and then ask.
Yes, yes. Yes, please. Hello.
Sanjay Kumar, you can ask. Or you can.
Or message also in the, you can put a message.
Yeah, message also, yeah.
There is Q&A chat, right?
Q&A is
yeah.
This one, yeah.
Is there anything?
You just raise the hand and then you just loan time. Okay.
Maybe we can ask in the.
Yeah, maybe at the end he can ask, yeah.
Okay. These type of blurs, they are used to reduce the noise. So what type of noise actually? The noise can be a broken edge. The noise can be a fused grain. The noise can be an edge grain. And the noise can be a salt and pepper noise. Just now I showed, right? In an image, there are a lot of small dots. So we call it as a salt and pepper noise. They are random white and black pixels. And they are not, in fact, contributing to the actual measurement. They are noise factors which can mislead the algorithm. Okay. So noise refers to random variations or distortions in an image, often caused by some sensor error or some pure lighting conditions or wrong measurements, manual measurement. If you don't take the figure properly, also it can come in, right? So they are the noise, and blurring, it helps reduce the noise by averaging or smoothing the pixel values. As I told you, the image is bright, and I say that you blur it, right? So you may think that it is a wrong method of doing things, right? But sometimes if there is an error, we say that if we find that there is an error, and which obviously will have a different intensity than the image, say a small dark spot will have a different pixel intensity than a white spot, correct? So how I will avoid that? Then I have to make both the intensity to almost to same level. That means I purposely either increase the intensity of the black spot to white, or purposefully reduce the intensity of the white to black, correct? So I'm averaging or smoothing. So blurring, it helps reduce noise by averaging or smoothing pixel values over a neighborhood, effectively removing random pixel variations that are not part of actual image count. So if you don't do this, that small dot, that also will be considered as our output, and it will show more number actually, right? But if that is not the case actually, experimentally when you find out that is not the case. So this type of what is that, blurring operation, they helps us to avoid this type of problems. Another important thing is edge detection. There are algorithms like Sobel, Canny, like that. I have a code on that. That also helps you to identify whether it is an edge, whether it is a boundary, like how we find this algorithm, how it finds basically whenever there is an edge or a grain boundary, the intensity varies. That is how we get a boundary, right? So the grain boundary will have a different intensity than your inside image intensity. So these algorithms, they compare the
Sorry to
intensity.
interrupt.
Yes, sir.
It is not in the full slide mode. I think it became small, and we can see the next slide also.
Okay. Is it okay now?
This is now good.
Yes,
Thank
yes,
you.
yes. Yes, sir, yes, sir. Likewise, for each and every shortcomings that I said in image segmentation, we have certain shortcomings and we have the solutions too, and we have applied. Now, before going to the actual application, as I told, let us create a small signal and try to put in whatever I said into that system so that we'll understand what exactly we are supposed to do. So what we will do, we'll create a small step signal. You know, there is a step signal up to 45 or something. There is a blue color line, it goes vertical and it goes horizontal. This particular case study I have taken from the source that I have mentioned. The participants can take a snapshot of this and you can go to the website and this medium.com, and they have lots of such case studies actually. This particular case I have taken from that particular source. Okay, and they have given some partial code also. Most of the times some of the codes are not running, but the smaller codes anyway I can share with the organizers. They can, I believe they can share with you. So we create a small step signal, and our idea is to purposely create a noise to the signal, then again try to avoid the noise, correct? So that is a good signal, obviously good signal. If the microstructure everything is good, I don't have any problem, right? There are a lot of problems, that's why I try to overcome that by putting certain commands. So here also there is a good signal, I purposely want to put a noise. So the command that is used to do this is this random.seed. This particular value creates a random number and add that to the step signal. Already there is a step signal and random value it puts it. The seed says that always any number of times you run, it is always the same random number that was generated first time, it will be repeated every time. Okay, that is the only difference. Otherwise, this particular code, it has a signal, it is auto generated by using this particular third line of the command. Then in that we add some noise signal. So this is a noise. The previous step signal has been noised now, it has been distorted now. Now I want to smoothen it, as I told you, the blurring signal that I told some time back, right? Similarly, I want to apply certain filters and I want to smoothen it. One such filter is called moving average filter. In a moving average filter, the signal, you know, it is varying in a random wise from left side to the right hand side extreme corner, the signal varied, correct? So this particular algorithm takes a particular value. We have three moving average method, 5-point moving average method. Like that, there are different types of moving average method, 3-point, 4-point, 5-point, like that. That means if 3-point means we take the 3-point nearer to 3-point, 4-point means 4 signal points we used to take. Okay. So in this particular case, we are going to blur this particular image by using a moving average filter. So what it does actually, it creates a small kernel. Okay, so kernel is nothing but the filter that I talked about, which will mask the pixel in a particular area. So there will be a big microstructure. We randomly choose a small area and put this mask over it. And underneath the mask, we'll have pixels of different intensity, and we try to normalize that particular intensity by an average. In this particular case, already I told you blur Gaussian, I told you median, and this is a new one, it is a moving average. So in this particular case, the noise signal which is having some noise, a signal which is having a noise, I would like to normalize it by using a moving average filter. So I'm going to use two different types of moving average filters based on a window size. The size of the mask that I'm using, it is 5 by 5 and 10 by 10, just to understand how it behaves. Okay, and this is the particular signal that I have received after using the moving average method. So basically, what this moving average, as I told you, it takes a signal and it keeps on averaging it moving forward. Say for example, we have at a particular location, the signal is like this 35286. This is a set of signal that we have got. So moving average, what it is, this is a 3-point moving average system. You take 352, the first 3, you average it. It is 3.33. Then the next signal, you start with 528. It is 5. Then you take 286. It is 5.33. Now there is no more data, so it stops. Now the approximation of 35286 is, it is 3.33, 5 and 5.33. Meaning there was a signal with an intensity of 8. There was a signal with the intensity of 2. There was a signal with intensity of 6. All I am averaging or smoothing it with a new signal of magnitude 3.33, 5 and 5.33. Correct? So how I have done actually, I have taken a small kernel. Kernel is, it is like a mask. I have put it on a pixel. Okay, so the process is like center a kernel on a pixel and multiply the pixels beneath the kernel by the corresponding values in the kernel. Then sum all the results. Replay the central pixel the summed value. Just now we have got 3.33, 5, 5.33. You replace the center of the kernel with the new data or new pixel value. Okay, this step, that whatever I have explained, it is also called as convolution. Okay, convolution. So what it is, the first step is you take a kernel or a filter. It is a small matrix. It is not something like that. It is a matrix, actually matrix of numbers, like 3 by 3, 5 by 5, 7 by 7, like that. There can be of kernels of different sizes, and we put it on the image, and it is like a cover. It is covering a particular pixel value, and each value in the kernel is multiplied with the corresponding pixel value in the image. And if you have a 3 by 3 kernel, if you center it on a pixel, you will multiply each of the 9 pixels. You know, there will be a center value surrounding that. There will be 8 points actually. So you will have 9, center 1 and the neighbors 8. You multiply your pixel strength of the kernel with 8 neighbors, and you find out the value. You sum it up and find the average, and that average you put it in the center. Correct? Understood? So yes, a particular spot having a lot of intense values, you keep on trying with a moving average value by taking additional points. You try to smoothening it and try to make it bit normal. Okay, so that is how it is done actually. So this is how it is. So there was a noise, there was a signal, and there was a noise, and we have used convolution algorithm, and it is slightly smoothening now. It is following the same pattern, but its intensity has come down. Correct? This gold color thing, it is slightly smoother than what you had earlier, right? So
what about the loss of information, sir?
Which one?
While capturing this, we are reducing the pixels, right? I mean, we are...
Yeah. Actually, it it iteratively use all the signals actually. It iteratively use all the signals that is kept. We are going to take only a small particular pixel strength, and within whatever is from the big image, we are going to take a smaller one, and the one which is coming to average. This method is average method, so it is coming to average, correct?
Okay.
If it is a Gaussian, so it is an average actually. Obviously, on the average value only it is takes, correct? There may be some upper limit and a lower limit. It is not taking actually. So obviously that should go off, right? Got the point or?
Yeah. Okay, sir. Okay, sir. Carry on.
Okay, so what you understood actually, so from these results we can conclude that increase the kernel size leads to smoother signal, right? So if you have a bigger mask and take into consideration a lot of points and try to smoothen it, obviously you will have a smoother signal. And because the larger signal takes in consideration a lot of neighboring pixels while determining the new value for the each pixel. And there are few drawbacks actually. The thing is that it works on lot of pixel points, so it keeps on calculating. So the code becomes a bit slower. And if the kernel size is disproportionately large, also it gets into some unwanted segment of the problem. That again adds another noise to the system. Okay, so we have to optimally use this system. So this is the signal actually, the original signal, then smoothened by moving average, Gaussian, and median filter. So whatever we have studied on a single small signal, line signal, let us try to replicate on original big image. Slightly we will move forward. So on the left hand side is the original image. As you will appreciate, there are a lot of ports, lot of unwanted pepper and salt type of errors inside. So we are going to purposefully destroy this image that is called as pixelated. Okay, the line of code pixelated in the previous command. Okay, I think somewhere I have kept it selects only every tenth of the pixel, meaning it purposely reduces the pixel strength of the image. That means the image won't have enough pixels to coin together and produce a proper image. So it will be distorted like this, just like we produced what is that noise in the line signal. And let us now apply the filters that we just saw. That is mean filters, Gaussian filters, and 3-point, 4-point filters like that. Let us try to put these filters on it and find out how it works on it. And we'll also compare the output given by each system, because each system works on certain concept. In the median, it takes only the median value. The Gaussian, it takes the center point, the highest intensity, and the farthest point, the least intensity. Right. So each and every method it works on a different method. So let us try to do that. And of which we have found that the mean filter is a very simple smoothing technique. It is used to reduce the noise. And this mean filter, it also can estimate the background color by averaging the principal values of neighboring pixels. As I told you, mean is you several number, you take the sum of the mean and replace the existing pixel with the mean pixel magnitude, right? That is the easiest and the simplest system. But however, this mean filter is not good for the edge detection. What it does?
Excuse me, Professor. Sorry for the
Yes,
interruption.
yes, please. Yeah, please.
Sir, actually, this Gaussian, like Lorentz, this is the fitting the curve. Is it that is okay, sir? From my understanding.
No, not like that.
Like
actually.
where suppose in XRD image where we fit the Gaussian curve like that.
Yeah, that is curve also fine. It is there. Gaussian curves are there. So this algorithm, what it does, a Gaussian curve, there is a peak, and the value it goes from the mean, correct? Sigma 2, sigma 3, sigma like that it goes, correct? So this algorithm uses the peak value, okay, and it gives that peak value to the center pixel, and as it goes away from the center, it gives lesser magnitude to the remaining pixels and finds an optimum value and replaces that. It is whatever you said is correct, but that this algorithm makes use of that particular concept. Okay.
Okay.
So that it tries to normalize the magnitude to a certain small understandable or acceptable range of magnitude. Okay. Now this mean filter, coming back to the mean filter, I said that all the neighboring pixel magnitude, it takes the mean and it replaces. Now unfortunately you have gone to an edge, let us say. Now the edge also, there is a huge magnitude. It takes the neighboring pixels magnitude, and the edge, it will have a higher magnitude. It takes and averages. And what happens actually, the edge will disappear. And we won't have anything to see actually. You'll have either a very dark image or you will have a very white image. I have purposely kept an image which has this particular problem. To avoid that, we have some algorithms like Sobel, Canny, Laplacian filters like that. We have a few methods to eradicate this particular problem. So these Sobel, Canny, and Laplacian, they are also called as derivative filters. They quantitatively measure the changes in the pixel brightness in an image, and they are used to enhance the contrast. They are used to detect the edges and the boundaries, and they are also used to measure the feature orientation, how it is oriented, how this, for example, a grain is oriented. Maybe you can use this algorithm to find out actually. How it finds actually, basically, this Sobel derivative, it is a derivative filter. It finds the edge, or, whenever there is an edge, the area closer to that particular edge will have a significant intensity change. Am I right? That's why we are able to see a boundary or an edge. So what it is, this calculates the rate of change of this pixel intensity from an inner region to a boundary region, and it finds its rate and it detects whenever there is a significant variation, then it comes to a conclusion that there is an edge, and that edge should not be destroyed. If I destroy, then two grain will merge. I cannot, in fact, count the numbers, and I cannot come to any meaningful conclusion, correct? So edge filters, they are all derivative filters. It finds the change of the intensity from one to another. Whenever there is a significant increase, obviously there will be, whenever there is a grain boundary, will have significant intensity variations. When that happens, it says that that is a edge. Okay. That is how this particular Sauber-Canyon Laplacian filter use. So I have a small code to test this particular process. So basically, yeah. So we have the original image on the left hand side, and we have the Sauber filter. It clearly identifies the edge. You will appreciate. We are able to see the boundary, right? So all other things it gives with the same color, but only the boundary it is slightly white in color, right? So slightly different algorithm is the canny edge detection algorithm that also puts still brighter images with the intensity variation very clearly marked down. Whereas this Laplacian filter, as I told you that I'm using only the existing models, correct? So the challenge, anybody who can slightly use Python can also use this particular concept. Only problem is directly when you use this particular built-in models, sometimes it won't work because, as I told you, there are certain thresholding factors, correct? And I have told you that sometimes there will be some intensity variations. So all those things have some parameters to adjust. Built-in, some algorithm they automatically adjust, and some parameters we have to do by our own iterative manner we have to give. That's why this particular Laplacian filter, it has not predicted anything. It has simply blurred everything, correct? It has simply blurred everything. But after slightly adjusting the meta parameters within the algorithm, some values inside, now slightly this particular thresholding, it has improved, right? So this threshold is nothing but you say to the algorithm, beyond certain limit, this is acceptable, and below that it is not acceptable, like that you just tell. So based on that particular observation, it assumes that I'm okay to consider this as a inner part, I'm okay to consider this as a boundary part based on the meta parameters that we have defined. Okay. So now because of that, we are able to get a bit of output. Previously it was extremely deteriorated, either it was very white or it was extremely dull, right? So this is how we do. Okay, we have taken a smaller signal, we noised it, then we denoised it. We have taken a figure, we have pixelated, meaning we have deteriorated it, and again we have applied this type of filters, and we have tried to go back to achieve the original figure. More or less we have achieved, okay? But if you set all the parameters properly, it will definitely it will give almost like the original figure it gives. I have taken this only as a sample figure, so I have not put properly the parameters. I will show the original problem that we have published in the papers. That you will see very clearly the grain boundaries, segregation, all those things would have happened so nicely. Okay. So summary, what we have done, I have just told. Now let us move to the next important topic, that is image segmentation. So what is segmentation actually? It is partitioning an image into distinct regions based on certain criteria. It can be color, it can be texture, it can be intensity, it can be size. There are several. Okay. So meaning there is a big image, you divide that into smaller image segments and classify it that this belongs to this belongs to this, like that. So let us go to the problem that I said that I will show you. This is the one that we use in the publications. What we do actually, there is an image, RGB image, okay? And that RGB image, we convert that into grayscale. Grayscale will have an intensity ranging from 20 to 255 in a gray. In the gray itself, it will have this much of intensity. Then as I told you, we will be using the blurring technique. I have explained why blurring is needed in the previous thing. So we blur it. Then when I blur it, as I told you, what is the threshold to which I have to blur it? What is the actual image that I need? What is the image that I want to discard? That I have to take a call, correct? Otherwise, it will fully blur into white or fully blur into black. So I have to have some thresholding. So I will set a thresholding. There are few methods, OTSU, contrast limited, histogram, equalization, like that there are few methods. So I will do a thresholding. Once the thresholding is done, the microstructure, I will clearly show which is the grain and which is the background, okay? But sometimes it may not be also. So what I do, I do a process called erosion and dilation. See, I have a lot of small grains. Inside that again I have a lot of pepper and salt type of errors. So there is a white image. Inside that I have a lot of dots. Now what I have to do, actually, this small dots should be eradicated. Means it should be eroded. It should be eroded. It should be disappearing. So that process we call it as erosion. Then the white part should improve in size. That we call it as dilation. So erosion and dilation I will do. Once the erosion and dilation is done, then we do a process called binary fill. What is binary filling actually? So wherever there is a boundary, we fill it actually. If we fill it with a particular color, green, yellow, orange, or whatever it is, we fill it with a particular pixel value. Okay, that we call it as binary filling. Then we also remove the edge grains, because edge grain, there will be very smaller grain will be there. There may be bigger, 1/2 will be there, 1/2 might be there, 1/4 might be there. If I take that also into consideration, my figure may give, my calculation may give wrong answers. So I purposefully remove that. Then I do classes division. Classes division means what is what. Okay. Then I connect classes of same thing together and I count it. Finally, I'll get a grain size measurement. I will say this is the number of grains present, each grain, what is the size, what it is, all those things you will get. So let us go one by one. So let us go to a particular code, so which takes an image. Okay, it takes an image. So this is the original image. This is the original image. The original image is also a grayscale. So same thing. If you take, for example, if you take a colored image, let's say.
That's the chain.
Yeah. So this is an RGB image, and we have taken a grayscale image. So why we have to take a grayscale image actually? Because the actual RGB image will have a lot of variations in color with a lot of intensities. So working on very large variations of intense images is tougher than having a smaller variation of intensity, correct? So that's why we try to simplify this image. So we try to change the RGB image as the only 3 color channel, the only single color channel. So we try to make it into grayscale. And we also this particular changing from RGB to grayscale is also done for cases like for many segmentation tasks, particularly finding the edge or the texture or the intensity. It might be relevant or it may be important. Okay. So color information might not be necessary, but I want only the intensity variation from within the grain and which is on the boundary. So I'm now more interested whether within the grain what is yellow or green or orange, but I'm only interested what is inside, what is outside. So inside can be white, outside can be black, or inside can be black and outside can be white, right? So I'm not interested in what is happening inside. I'm only interested is how much is inside and how much is a boundary. So I don't want a color figure at all. So I feel that it is better for me. I have only a RGB. And again, another thing is I said that the algorithms like Sowell and Canny, they find out intensity variations between inside of a grain and its boundary, right? So they feel for these algorithms, grayscale is better. Instead of having very large intensity grains and confusing these algorithms to find out which is a boundary and which is not a boundary, and if we have a lot of intense variations, they may think that inside the thing also that it will draw a lot of lines saying that there is a boundary, right? So for the sake of edge detection also, I want to convert this particular figure into a RGB. The next important thing is the median blur. So again, we take the same image. And apply the blur. So you will appreciate that this is a bit clear image, and this has been purposefully, it is blurred. I have told multiple times why we do this what is the blurring operation is to enable that we have avoid unwanted process induced errors within the object and smoothing them into a normal image, correct? So we have used several methods like Gaussian, median, all such things. So median blur, it is the commonly used image processing technique. It is done to improve the quality of the images and the performance of the segmentation algorithms. Particularly, it is done to do noise reduction. As I told you, salt and pepper noise, which is nothing but the dot spots available in a white background, lot of small dots, that we call it as salt and pepper noise. It is a common issue in any image. Everybody will, those who have taken will say, appreciate that. That is one of the problems for them. And especially when they are captured with low quality cameras or doing image transmission, this type of errors comes. And this noise appears as random black and white pixels, and it will be scattered across the image. And median blur, median blur is particularly effective in removing this type of noise. So it works by replacing each pixel with a median value of its neighboring pixel, which helps to smooth the image while preserving the edges. So as I told you, only wherever there is an intensity variation, it works. So edge is having a huge intensity variation, it won't work there. So it still preserves the edge as well as it removes the salt and pepper noise also. And edge preservation, so unlike other blurring techniques such as glossy and other things, which also potentially can blur the edges and other details also, median blur, it helps preserve edges. So this is one of the beautiful method we can use to blur. So we have a small code again to find out how this works. So we'll use the same thing. Yeah. So this is a median blur, and I'll also open a colored figure. Yeah, we'll go back. We'll take a lot of time. Yeah. The next one is, as I told you, now we have blurred the image. Now I have to use an algorithm to rationalize or to equalize or smoothen it, all those things. For that, I need to understand which is needed, which is not needed. So one of the methods that we use for this particular thing is called thresholding. So we have different types of thresholding algorithms. One of the beautiful methods, as I told you, is OTUSU method. Thresholding, it converts a grayscale image into a binary image. Grayscale image will have intensity variation from 0 to 255. In a binary image, either will have 0 or 1, right? So either it is dark or white, black or white. So thresholding, it converts a grayscale image into a binary image, where pixels are classified into two categories based on the predefined threshold value. Typically, pixels with intensity values greater than the threshold are considered part of the foreground, and those with lower values are considered part of the background. What is foreground and what is background? You take a microstructure, there will be a lot of grains, right? And that we need. And what is in the background, that may not be needed, right? So whatever that is visible, you take it, and not needed, you discard it. So the one that is needed is considered foreground, which is not needed, we consider as a background. But how the system will identify that is foreground or background, that's where the thresholding comes. Sometimes this thresholding value is given by the user. Some algorithms, they iteratively they find out the thresholding also. Okay, so in our case we have also done a lot of iteration and we have found some suitable thresholding. And thresholding also can help you identify the edge as well as boundary. So it simplifies the boundaries of the regions in an image. So that will be helpful when you do edge detection. Okay. The next one is erosion and dilation. As I told you, erosion, it removes small noise. What is a small noise? The beautiful example is for pepper and salt noise. There are a lot of small dots. So I don't want that, right? So what it does, this erosion algorithm, it helps remove isolated pixels or small artifacts in the binary image, such as salt and pepper noise. And after identifying it, it reduces the sizes of the foreground, the white region, by shrinking their boundaries. So we have a lot of small dot spots inside. This algorithm, it shrinks the white space. So while shrinking the white space, the small dot spot will be under pressure, correct? So it will be under pressure, so it will be eliminated. So small unconnected foreground regions are removed or eroded. And after this, I cannot simply keep it as such because you are not getting the actual size. You have purposefully reduced this using algorithm, right? So what you do, you again dilate it. So again you enlarge the white portion, okay? So it dilation algorithm, it enlarges the foreground boundaries because to eradicate this small dark spots, purposely you you reduce or shrink, right? So this dilation increases the size of the foreground or white region, effectively expanding the object boundaries. And again, it fills the gaps between the segments, small gaps or breaks between connected parts, it fills it. And it also will be useful when segmented object is too thin or fragmented. If there is a small fragment in the grain and you know that it is part, but the system cannot understand. This type of algorithm, dilation algorithm, it also helps you to makes it part of your system. Okay, it takes into it. So it also restores thin or fragmented objects. So what it is, you are filling the holes, then you are enlarging the image. We call that as erosion and dilation. And then you fill it. Okay, so whatever image that you have, a small hole or something, you fill it with a particular value pixels. Okay, so binary hole filling refers to the process of filling the small gaps or holes within the foreground objects in a binary image. These holes are typically surrounded by the foreground pixels or the object, but they represent regions that are not incorrectly classified as background due to the noise. So basically, whatever is needed for us, it fills it. That is the algorithm, binary hole filling. So we are taking a binary image. The binary image will have only 2 pixels, either 0 or 255. The foreground object, that is the object that we want, let us say that is a white one, value of 255, and a background, it is not needed for me. I say that it is a value of 0. So how we identify that something is needed for me and something is not needed for me? Basically, a hole is the one that I don't want, I said, right? I want to fill it. So how I say that is a hole? So a hole in this particular thing is a binary image that refers to a small region of background pixel, let us say a value of 0, that is entirely surrounded by a white one. Correct? No? So it is entirely surrounded by a white one. Somewhere here we have smaller black spot. I want to fill it. So it identifies and it fills. So how it fills? There is an algorithm actually. A famous algorithm is called as flood fill algorithm. So this flood fill algorithm, it fills wherever the background image 0 is there, it fills it with the foreground image. Meaning it fills with the white color on the black spot, so that all this disappears and you will have only a foreground pixel on the particular image. I'm going a bit fast because I need another 10 minutes time. Then edge removal, this is also very important. As I told you, we have a lot of algorithms to find out the edges. And let me take my pixel and my figure. As I told you, this is the original, the leftmost is the original image, this one is a blurred image. And this two figures, it is not exactly giving you the proper figure, correct? That's what I was telling. See, Python is having a lot of modules. If you simply use a module and run your code, it won't work for, sometimes it works luckily, but sometimes it may not work because you have to set in a lot of parameters inside. That you can do it by seeing the output. Where the error is, you find out, then accordingly you have to set the internal parameters. A lot of parameters you have to adjust. I'll show you the same figure. I'll show you the end result in a beautiful figure after 5 minutes. As of now, what I would try to stress is, you need not spend your, you need not be too brilliant to develop an algorithm. You need not spend a lot of time developing algorithm to make sure the edges are visible and the images are blurred. All those things all are available in Python. You can use it. Using that itself, you can publish papers. And the good thing about machine learning and artificial intelligence is not many have published papers. So even with the available set of technology that is available in Python as well as other AI techniques, we can publish papers provided you are a bit faster. After some time, if you come people like me or Professor Nalnikant or Rajesh, they will publish papers, and after some time, people will expect more from us, right? So as of now, it is very nascent. We can do it. Only thing is, straight away, it won't be kept in your plate. You may have to do a split of small, minute changes here and there in the parameters. As of now, purposely I have kept this figure because to emphasize that, what is that? These things are needed to be done. Okay. Yeah. So with this, what I will do, I'll go back to the algorithm that is fully finished. Okay. I'll directly go to the algorithm. I think. Sorry. I put that wrong. So is it fully visible or only partly visible?
It's.
I think it's fine, right?
Yeah, it's fine. It's fully visible,
Yes,
sir.
yes. So what we have done till now, we have defined what is ALML. We have defined what is an image processing. We have taken a very small signal system. We have purposely deteriorated its quality. We have applied a few algorithms to better its properties. Then the same algorithm we try to put it on an image. Then we have taken another set of image, and systematically we have done some exercise. What they are, we have done some grayscaling, we have done some medium blurring, we have done some thresholding, we have done something called erosion and dilation, and we have done some binary filling and removing the edges. We have done some class divisions, we have connected those things, and we have tried to count the grains. Okay. Now, as I told you, I put a very raw code in the previous slides. Now I will show you a code which runs bit better. Okay, so in fact it should be better because with this only we publish paper, so obviously it should be better. So this is our Gaussian blurred image, and this is the Clauhy thresholding algorithm, and we also done a OTSU thresholding algorithm, and we have done the erosion. What is erosion actually? You remove all the black spot by shrinking the white spot, right? So that is erosion. And dilation is you try to again increase the white spot, and you fill the hole. Even there are small spots available. Now it is disappeared. If you, I think I have closed that image. If you have seen that image before, you still had certain black spots in between, right? So that has been filled now. And we have done a thresholding. I didn't explain that concept of OTS and other things. In fact, that works like it finds a histogram of the pixel strength within that domain, and it takes an average and takes at as a threshold actually. So this is a thresholded image, and the original image histogram is like this. It was having lot of variations. But after the thresholding has been done, we are choosing only one thresholding, correct? And this is the, as I told you, labeling. So once the erosion is done, one dilation is done, once filling is done, you put set of no dimensional data into it and give some color coding to it, so that later on when we count the image, we can easily count. So that's why we have given some colored labeling to it. And we have removed the edge. As you can appreciate, on all the edges there were grains actually previously. Now it has been removed, right? So it has been removed. And now okay, so hearing. Yeah, so this is what we have done. Yeah. So now all the it is visible. No, the foreground is visible now. Now the code counts. Okay, so it counts. So it says what is the grain size and how many grains are there, and for each and every number, what is its area and what is the fraction with which it is composed of. So all such information it gives. So for all the counted grains, it gives the area actually. Okay. Now by that way, now we can in fact um, uh, measure the grain. We can prepare a sample that is good enough, avoiding all the inherent problems, prepare it, you do all the polishing work and give to the system. In fact, I was uploading an image, correct? So you straight away, you take a microstructure and bring it to the system, you upload it, and it gives all the relevant data. Still, there are a lot of things we did actually. I have shown you only very small area. This is how we can use different techniques available in image processing, and we can measure this thing. And what we can do now, I have got lot of grain sizes, correct? And that grain sizes I can use for a supervised machine learning. So can I have another 5 minutes, sir? I'm already running late,
Yes,
I
sir.
believe. Yeah, another
Yeah.
5 minutes I'll
5 minutes, sir.
conclude.
5 minutes.
Yeah, 5 minutes I'll conclude. So this is one of the recent papers we got. It was accepted in ASME. In fact, I did not take the grain size here. We took the flow stress of metal forming problem, one particular thing that was formed under temperature, different temperature, strain and strain rate, and a particular output. And we use a lot of machine learning algorithms, and all these algorithms we use, and we ran the code and find out how it performed. Okay, which algorithm suits our particular problem, like that we found out. Again, this command prompt, this command prompt unnecessarily it is getting disappears, it is not there. So basically, there are, as I told you, there are a lot of built-in codes available. So for example, let us say random forest. So with the flow stress data, um, uh, we take the flow stress for different stress temperatures, different strain rates, and we find out how it predicts. So based on the model performance, whether it is 99% or 98% or 58%, we conclude which particular algorithm will predict things properly, like that. That is on ML algorithms, how to predict things. So with that, there are a lot of algorithms. Time is running out, and if I rush through also won't be good. So that if I complete now, we have some time for what is that discussion also, right? Yes, sir.
Question in the chat. Can you see the chat, sir?
Which one, sir? Yeah, okay, I'll do that.
क्वेश्चन पूछना होगा नहीं how exactly
if you want to measure precipitate size, yeah, we can same the algorithm can't differentiate between a precipitate and others, right? So it only sees the magnitude or intensity of that particular object. So we can, and you know this precipitate will be of this size, then you give a particular color coding to that after it is filled. And if it is after eroding, dilution and filling, you give a particular color coding, and we can measure. Obviously, we can measure. Okay. And is there anything? The explanation considers that you can do this or that. I don't understand what it is.
No, the bottom one, sir. If you're looking at the previous session, yeah. Come down. Yeah.
Yeah, you have put much effort into making it more practical with evidence and okay, fine. Thank you for the comment. Yeah. Is there anything you can ask me?
Oh, sir, I have a question.
Yes, please.
So this is regarding the image. I mean, the resolution of the image. Let us say, even if the nano microscope image is also compatible with this model.
Yeah. So as I told you, anyway, purposely we are making it out of focus for certain purpose. So when the image itself is bad, also obviously it should work actually. We have not tried on that. We have taken some good image only. But if the image is too bad and if the boundary is not visible properly, okay, and the edges are not visible properly, obviously we cannot use this. If it is so dull, at least there is some intensity variations, then obviously we can do it and we can brighten it also. Okay, the image also, from a very dull image we can brighten it also. But there should be a considerable intensity variation between a good one and the inner one and the boundary. Then only we can.
So it is a microscopic, specific modeling, right? I mean, let us say if my data, if data should be taken from the same type of resolution microscopes.
No, this particular algorithm will work on any image. You take a photo of yourself and you put also it should in fact. Okay. It only identifies the boundaries, correct? So it's the outer boundary and the inner. It should be suitable for anything, but we are using it for our own applications, which is microscopic images. So I have explained with that. We have not tried it. It should work. Maybe there may be some small modifications we may have to do.
Okay. Thank you, sir. Thank you very much.
Sir, I have one follow-up question.
Yes, sir. Yes, sir, please.
Finding other surface properties like surface roughness, tortuosity, we use the same algorithm.
Yeah, so maybe we may have to modify it because this one identifies the edge and the non-edge, correct? The main, the center point of this algorithm is to find the intensity of a center portion and you ensure that it is moderated or smoothened. Then after smoothing it, you find out a huge variation in intensity and not so good, so that you say that is an edge, right? If such characteristics is available in the picture, I think this algorithm will work. Other things we have never tried it, we can, but we have to maybe work on it a bit. We have to find out how it works. Some algorithms might be there. As I told you, we started only 3 years back. At least my students, I don't know. I knew nothing about machine learning in 2022. Okay, zero. But still, when my student said he wants to use, I said, okay, we'll go ahead. So I attended a lot of courses. I attended a lot of YouTube videos we saw. So I did with zero only. I am now also I will say that I have come from 5% or 10% of the knowledge level only. We can, if you put effort, I think there might be some algorithms which can suit your need. We have to see literatures and we have to find out.
So what I understand is like from working with biology, with stem cells and other, these techniques we normally use for cell imaging, live cell imaging kind of thing. And the most of the imaging, microscope imaging softwares, they employ all these techniques to provide us a good image.
Mostly, yes. You are correct.
Most of the
Yes,
softwares, like for example, if you take any confocal microscope, even for this, for the matter scanning electron microscope, if you take it in a two-dimensional, it will enhance everything and then give that.
Yes.
So these kind of,
the first part is what you said, sir. Image processing is what you said. But the later part, that I didn't have time to explain actually. So the later part, I have just identified one, right? So I will train the system with hundreds.
Yes.
I will train the systems with thousands.
Yes.
Small segments from the structure. Then later part, it will be able to tell what it is.
Exactly.
But your microscope won't tell, right? It only gives
the microscope won't tell. Now, for example, this kind of been just to give, I'm not saying, just to give the broader picture kind of thing in the field of biology and healthcare. For example, more specifically in the healthcare, especially in corneal image and all. Okay, so whenever they take the snapshots of the cornea, so based upon the image itself, they will predict and then they will tell. The later part which you said, right? They apply it and then they will tell whether this is having whether this image is proper or whether it is having a disease or not, based upon the image only. That kind of prediction.
So that also predicts.
That also predicts, yes.
Okay. But what they use actually? What is algorithm they use?
Same whatever you said. Each of them has their own proprietary algorithm.
Yes.
Okay, say for example, breast cancer. They take any CT scan images kind of thing, and then they have advanced image processing techniques and then predictions tools. They compare it with so many actual patients with the healthy patients, and they will able to predict whether this patient is having or chances of breast cancer or not. That's why I'm just telling. In
Mostly
other fields
actually
being widely used, I'm trying to tell you. That's it.
Yes, sir. In fact, I studied that. They in fact started with medical imaging only.
In medical imaging, yeah.
They started. Later on, slowly we are adapting. Maybe Rajesh sir may use for surface roughness sometime later also. So it is evolving in fact.
Yes, sir. Thanks.
Whatever you said, 100%, sir. That is true.
Yeah. Any questions? So there's one more question is there, sir, in the chat box.
Okay.
How many images
we need to give us input data to get accurate output, sir?
So this is in fact, as I told you, this we are only one image we are doing and we are identifying. But if you want to predict, I think we may have to give data in a vast varied domains of process conditions. See, we use it in metal forming. We do for with different temperatures, strain rates, and parameters, material parameters we vary and take the process data. Okay. For each and every variation, you will get a different structure, right? So if you want to predict, then for a data set which we are, as I told you, we are doing supervised learning with classification. So obviously, there should be a one-to-one correlation. So whatever process I am doing, that should have a output. So that means equal number of minimum at least one. In fact, more is needed. Minimum at least one, then only at least you will have a result, right? And it depends on its accuracy level also. So if you want to do this as a prediction, I have not given this as a prediction model actually. If you want to have as a prediction model, then you may have to have lot of data which has some amount of correlation with your process. Is it okay? Or?
Yeah, okay, sir.
Yes, there's also another question is there, I think.
Yes, sir. Strain rate and residual stresses using this model. I think back propagation you can do. If at a particular strain rate, this is the structure you will get. That is a one-to-one correlation. So if this is the structure, this can be strain rate like that we can have, but directly we cannot tell. I think directly we cannot. We can back propagate, and we can assume that this may be that is possible, provided there is a strong correlation, and if there is a slow strain rate, this is a structure like that. If there is a strong correlation, then we can maybe predict. But that correlation is very difficult actually, because it depends on other factors also, no? Temperatures and other things. Is there any other? Nothing else. I think.
Yes, sir.
Thank you, Sir Davidson, sir. Thank you very much for giving time and sharing your knowledge here. It was very detailed explanation of application of machine learning. You explained even the algorithms, how we need to go step by step. That was very insightful. Thank you very much, sir.
Thank you, sir.
And yeah, so I am also extremely thankful to Dr. Nalinikant and Dr. Rajesh for inviting me. In fact, this is my first ATAL program.
Oh.
And in fact, I was a training and placement officer in my institute 2 years back. For the past this year, I'm relieved. So in fact, I did not give much presentations also, because I was busy with my placement activities. So in fact, I was worried whether how long, how depth I should go, or how basic I should go. Like that, I was worried. And Dr. Rajesh was guiding me. In fact, I made few changes. The one that I sent was a bit different. Yeah. So, and since the participants also of varied specializations, I don't know how far people were able to grasp. But as I told you, in 2022, I was zero. And myself and my scholar, we learned together only.
Yeah.
And my BTech student, he was, after he joined with me only, we were able to have some progress. So I have acknowledged them also in the thing, and it is anything can be, so provided we put some effort.
Yes.
And some good collaborative study if you do, definitely we can do. Okay. Thanks once again, sir.
Thanks, sir. Thanks
for the participants also.
Yeah.
So,
thank you, sir.
We will be sharing you the feedback from the participants, sir.
Yes, sir. Fine, sir. Then. Thank you. Then we'll meet you.
Nice to meet you, sir. Yeah. We'll see. Good night. Yeah.
Thank you.
Good night, participants. Yeah, we can join for tomorrow. Yeah. Don't forget to provide the feedback. Please provide the feedback.
Sure. Good night, Nayan, sir.
Yeah.